Hi guys, welcome to WeTeach. In this session we are going to discuss simplified inverting amplifier filter circuit of a low pass filter. Okay, in earlier session we have discussed it like active low pass filter with example. Now what is the simplified inverting amplifier filter circuit, that we'll see. So by using invert amplifier means we will use a op amp, operational amplifier. So this is the simplified inverting amplifier. Inverting amplifier means we will give the input to the negative terminal. So here it is negative, here it is positive. So we'll give input signal to a negative. So that's why it is known as a inverting amplifier. So this is the circuit, and here I am taking R1 as 10k ohm, and here capacitor C 10 nanofarad and R2 100k I am taking in parallel, because this will represent a RC low pass filter. Okay. So now here input I am giving a AC signal. So output also I am getting output as AC signal. Here is the capacitor has been moved from the op amp's input to its feedback circuit in parallel with the R2. This parallel combination of C and R2 sets minus 3 dB point as before, but allows the amplification gain to roll off immediately or indefinitely beyond the corner frequency. So at low frequencies, the capacitor reactance is much higher than R2. So the DC gain is set by the standard inverting formula, which is minus R2 by R1. So gain formula of this amplifier is minus R2 by R1, which is 10, right? For this example, as the frequency increases, the capacitor reactance decreases, reducing the impedance of the parallel combination of XC and R2. So this is the parallel combination of XC and R2. XC is parallel with R2. So if I reduce this until eventually at high enough frequency, XC reduces to 0. If I increase the frequency, my XC will be decreases. The advantage here is that the circuit input impedance is now just R1 and the output signal is inverted, right? So due to, if I increase the frequency, our XC becomes very low. That's why this is negligible compared with R1. Now our circuit has only input impedance, which is R1. With the corner frequency determining components in the feedback circuit, the RC set point is unaffected by the variations in source impedances, and the DC gain can be adjusted independently of the corner frequencies. So due to this, we can adjust the DC gain independently corner frequencies. Next, unity gain non-inverting amplifier filter circuit. So how will get the unity gain from non-inverting amplifier circuit? Non-inverting means if I'll connect source to the input to the positive terminal. So in to positive terminal we have connected to the source, which is AC source, and here I am considering R is 10 kilo ohm, and now I am bringing this RC parallel circuit to the negative terminal. So that is R2 is 9k ohm, C is 110 nanofarad, and here feedback path is R1 is 1k ohm, and the output is sinusoidal only. So here, due to the position of capacitor in parallel with the feedback resistor R2, the low pass corner frequency is set as before, but at high frequencies the reactance of the capacitors dominates the shorting out R2 and reducing the amplifier gain. So due to this connecting this XC LN or LNC parallel, RNC parallel at output feedback, so that will reduces the gain. At high enough frequencies, the gain bottoms out at unity, 0 dB, as the amplifier effectively becomes as a voltage follower. So the gain equation becomes 1 plus 0 by R1, which equals to unity. So that will become unity. So by making RC parallel circuit to the feedback, that will give the gain as unity by giving non-inverting amplifier. So application of active low pass filters are in audio amplifiers, equalizers or speaker systems to direct the lower frequency basis signals to the larger speakers, or to reduce any high frequency noises. So we will use active low pass filters to reduce the high frequency noises in radio amplifiers or audio amplifiers, equalizers, in some speakers, or high sound, high type distortion. When used like this in audio applications, the active low pass filter is sometimes called as a bass boost filter. So when we use in audio frequency range applications, this low pass filter is also known as a bass boost filter. Now coming to second order low pass active filter, as with the passive filter, a first order low pass active filter can be converted into second order low pass filter simply by using an individual RC network connected to in path, input as a path. So one active circuit series with another active circuit. So the frequency response of the second order low pass filter is identical to that of first order type. Expect the stop band role of will be twice the first order filters. So except stop band, it will be the twice of the filter, which is 40 dB per decay or 12 dB per active. Therefore, the design steps required of the second order active low pass filter are the same. So if I see the second order active low pass filter circuit, so that will be the, so R3, R4 which are connected in parallel. From here I am taking a capacitor which is connected to output port, and capacitor I am connecting here C2, connected C2 here from inverting non-inverting terminal to ground, and C1 is connected from R3 to output terminal, and here R1, R2 are connected as a feedback path to the output. So from here my gain is AV is equal to 1 plus R2 by R1, and corner frequency is equal to 1 by 2 pi square root of R3, R4, C1, C2. This is the corner frequency of second order active low pass filter. So when cascading together filter circuits to form higher order filters. So if I cascade filters in cascade mode, so it will get form higher order filters. The overall gain of the filter is equal to the product of each stage. For example, the gain of one stage may be 10 and the gain of second stage may be 32 and the gain of third stage is 100. So different stage has different gains like 10, 32, 100. Then the overall gain will be 32,000, which is 10 into 32 into 100, which is nothing but a multiplication of all three gains. That will give us a total gain of the three stages, which is 32,000. So if I take some example like cascade voltage gain, so first amplifier has a 10 gain value as 10, second stage has 32, third stage has 100. So if I write in dB, it will 10 gain means it is 20 dB, 32 means it is 30 dB, 100 means it is 40 dB. So if I want calculate total gain of these three stages, that will give us 10 into 32 into 100, which will give 32,000. So this is in gain, means normal value. So if I want to calculate is in decibels, so it will become 20 log 10, 32,000. So that will give us 90 dB, right? So 90 dB means here already we have seen 20 dB plus 30 dB plus 40 dB. Okay. So second order two pole active filters are important because higher order filters can be designed using them. So why this second order important means we can use higher order filters designed by using these second order filters only. By cascading together first and second filters, filters with an order value either odd or even up to any value can be constructed. We can construct any higher order filter by using this second order filter. In the next tutorial about filters, we will see the active low pass or active high pass filters can be constructed by using reversing the position of a resistor and capacitor in the circuit. So in next class, with this I am concluding. In next class we will see passive circuit, passive filters. Okay, thank you.